Let's get started. Alright, so welcome back. We are now in this class, at this point, done with supervised learning. We are moving to unsupervised learning. Today we'll look at k-means, something on Gaussian mixture models. We probably won't be able to get into EM, stands for expectation maximization this time, but that's what we'll do next. Okay. Your midterm presentations have been graded. You should have those grades already. That's what the histogram looks like. Most of you did pretty well. Alright, so coming back. So just sort of stepping back in this class, here's sort of the broad picture that we started with at the beginning of the class, right? So the idea was supervised learning, and all of supervised learning in what we looked at was just a mapping from X to Y. If Y was discrete, it was a classification problem, multi-class or binary. If Y was continuous, it was a regression problem. Right? Where we're going to next is an analog of this in some sense, but it's a setting where whatever you're supposed to map to isn't actually shown to you at training time. Right? That was the key distinction here, that at training time I show you X and I show you Y, or f of X, what would I like you to map it to. And here, it's going to be sort of, all you get to see is X. You just get to see a data set of X1, X2 till Xn, and clustering is going to be this idea of, loosely speaking, map, and this is sort of, loose analogs mapping to discrete IDs, and dimensionality reduction or embedding is going to be mapping to some continuous values. Right? The idea is going to be, in some sense, unsupervised learning is about learning something about the data set that is given to you without anyone explicitly telling you what to look for or what to map. That's sort of the idea. It's also going to complicate problems a little bit, because while supervised learning was an extremely concrete task, right? We knew what we were supposed to do, we knew how we were going to be evaluated. Right? At test time, somebody was going to come quiz you with an X, they knew what the Y was, they would check what you would predict, and you would pay a loss function. In both these problems that I'll describe today, it's unclear what is the end goal, why are we doing this? And in most of these cases, what's going to happen is we're going to have some sort of faint notions, some qualitative notions of what we'd like the end goal to be, but there are going to be different ways of quantifying that qualitative notion. Does that make sense? It will become clear in the context. So, at a high level, unsupervised learning is going to be learning only from X. So learning only from the data that's given to you, and the sort of two or three types. So we'll look at clustering, dimensional reduction, and the third thing, which I didn't show in the previous slide, is sort of density estimation, where instead of X going in and a cluster ID or some continuous value, you're supposed to predict what is the probability of X. Right? How likely am I to see this point? People often use this for outlier detection. Right? If I am getting a bunch of data from some stream, can I tell that this data point is an outlier? And this is an extremely rare sample. That's the one application of density estimation. So the general task is, given an X, tell me number, probability of X, how likely is this? How likely am I to see this data? Okay, so those are sort of three broad families of unsupervised learning, if you will. We are going to be starting with this idea of clustering. Right? And again, the pictures you're going to see about clustering are going to generally look like this, right? They're going to be this notion of somehow if I visualize my data in some low-dimensional spaces, there are going to be, each point here, this is a two-dimensional x1, x2, there are two features I'm measuring, and somehow what I observe in my data are different groupings of data points, right? There are many different applications for this. People want to often, ad companies want to sort of see what type of queries people type, and so what are the groupings of users that are accessing a website, what are different types of, so for example, Netflix Movie Challenge has sort of two types of clustering going on. There are genres of movies and there are types of users. Right? So you can cluster in the user space, you can cluster in the movie space, and you can sort of get different. So generally you should think of this idea as, what are the different types of my input? Initially, what we'll start with is this idea that every data point can have only one type. So it's going to be hard assignment. Right? There is some list of types. I don't know what their names are because I was never shown that at training point. At training point, there is no train and test, right? But I'm only provided just this, right? Just a bunch of inputs, and I tell you maybe I'd like to divide my data set into 10 types of users, right? Where 10 is just some number I came up with. or some k types. And initially we're going to start with this assumption that every user, every data point has only one type. So tell me an ID for every person. Right? The reason why this is going to get tricky is nobody's going to tell you at training time what type looks like, right? You don't get X, Y for every user. Okay, so the synonyms you're going to hear along these things, so obviously clustering, the algorithm we will first look at is k-means. If you hear terms like vector quantization, which is just another way of referring to the same thing, right? It's just hard clustering. If you hear the term latent variable models or hidden variable models or mixture models, it's all sort of referring to the same theme of works, which is going to be sort of clustering type algorithms. Does that make sense? Okay, so what we'll do is we'll start with something that I actually don't like starting with in my own research, which is let's take a procedural view of things. Let me first introduce an algorithm before telling you what the problem is, right? Which is an odd way of starting, but often it's sort of illustrative. So here's the input to us, right? This is our data set. Right? This is every dot here is a point in some two-dimensional space. This is our input. Somebody says, I think there are five clusters, five types of inputs, right? Just some k that they came up with. And what if I said, okay, here's my initial guess for them. I think this is cluster 1, this is cluster 2, this is cluster 3, this is cluster 4, this is cluster 5, right? They're garbage initializations, but they're okay. If I told you what the initializations were, can we assign a data point to a type? Sorry? K and N, but we don't even need K and N, right? We just need one nearest neighbor, exactly. So if you could just find for each data point its closest cluster center, right? So cluster type, right? So every data point, so that's why what I've drawn here is the Voronoi diagram, right? So on these lines, every point on this line is equidistant from two centers. Every cell, for each cell, every data point that falls in that cell will be assigned to this thing. So that seems pretty easy. We can do that. How about if I tell you an assignment of data points to cluster centers? Can we tell where that center should lie? Centroid, right? So if you tell me what points are assigned, so if you tell me that in this cell, these are the points that are assigned to this cluster center, we can sort of re-estimate a cluster center. Right? So we can say, all right, for these points, the center should lie here, not here, because the center of mass for these points seems to be here. Same thing for here, same thing for here, same thing for here. That guy maybe just doesn't move too much. Okay, and now that we've done those two steps, you just repeat. Right? So you have, voila, an algorithm. Right? So we didn't know what we were trying to do. We didn't know, right, what is this beast that we've just constructed. Each step seems reasonable. So you can implement this, right? You can already go out and implement this. Does that make sense? Yes.
When do you know that when it's terminated?
Excellent. So does this algorithm even stop? Or actually, when do you know it's done? What were you saying?
When the centers are no longer changing.
Yeah, so that's a continuous variable and the centers are not changing. It's an easier variable to check. Either. What? So threshold, what else? So there's actually a discrete variable in this problem as well, right? It's the assignment variable, because each data point we said was assigned to a cluster center, right? So for every data point, I have a discrete value, 1 of k, and there's n data points, so n discrete values. If those don't change, your estimates of centers can't change either. Right? So if every data point, you have two successive iterations of this algorithm. In both those iterations, if all data points are assigned to the same cluster center, then the new mean that you will estimate is from those same data points, and therefore you will converge. So we know the convergence criteria, but the question that is harder is, does this thing even converge? Will we ever get there? We know when we'll know if we're there, but will we ever get there? Does that make sense? Okay. So this is an extremely procedural view of k-means. This is the simplest way of sort of introducing k-means. But there's a richer way of understanding k-means, which is k-means is doing something. It is optimizing something. and we'll say what is it that k-means is optimizing. Okay? Yes?
Is it a common application to find a number of k, or you have to?
Yeah, so how do you, like,
Cross-value.
this is one point where that fails, right? So how do you find k in any
Yeah.
machine learning algorithm? Cross-validation. Except, what is cross-validation?
How can you
Exactly.
mitigate the error?
You don't have a task loss here.
Yeah.
So I didn't even say what k-means was doing, right? What objective function is it minimizing. We'll come to how do you pick k. In most k-means sort of implementations, if you open up MATLAB, it asks you what k would you like, and it will give you that many clusters. And we'll talk about how do you set these clusters into it. Okay. All right. So let me do this on. Actually, let me do this on. So sort of here's the notation that we'll follow, right? So we're given a data set. This time the data only contains x's, right? x1 through xn. So each one of these xi's is living in some RD. That's pretty standard. What we're looking for are cluster centers. So cluster centers, which are these parameters that I'll call mu1. So you're also given k, and some integer that is input to the problem. And we're going to define mu1, mu2, all the way to mu k. Right? Each one of them living also in RD. Right? So these are our cluster center variables. And what I'll call as my cluster assignment variables, assignment IDs. Sure, I'll say C1, C2, all the way till Cn, each one of them living in this discrete space. 1, 2, all the way to. That makes sense? So this one, there are k of these. For each cluster, there's a center that tells me where should I place this center on that map, right? This one is for each, there's n of those. For every data point, it tells me which one have you assigned this point to. Cluster 1, cluster 2, or cluster k. Does that make sense? It will be useful for us to sometimes think of these as discrete variables, and sometimes we'd like to think of these as binary vectors. So we'll do something which is fairly standard at this point. You've seen this. This is the 1 of k encoding. So what we'll do is we'll think of a binary vector. So a1 all the way to an. So there are n of these. Each ai is basically a vector of length k, and wherever, so if you want the third cluster center to be assigned, you just sort of put 1 there. So sort of like a 1 of k encoding. The third cluster, you put a 1 there, and so obviously there's a sort of this sort of a constraint aij is, it belongs to 0, 1, and the sum of aij over j is equal to 1 for all that. Does that make sense? So this vector has to sum to 1, and each entry has to be 0 and 1. And that basically ensures that there's only one bit that is turned on. Does that make sense? Okay. So what k-means is trying to do is it's trying to estimate these variables and these variables, right? That's sort of the problem here. We need to know where to place the cluster centers, and we need to know which data point to assign to which cluster. And it's actually, this is an idea beyond k-means, and you'll find this generally useful in your work. If you ever find a variable with sort of two kinds of, if you ever find yourself facing a problem with two kinds of variables, ask yourself, does my problem become easier if I know one set of variables? Right? And if that happens, then you can sort of set up this alternating minimization or optimization blocks. So if I know what these guys are, I can try to estimate this. If I know what these guys are, I can try to estimate this. And formally, we'll define this as something called a coordinate descent out. Does that make sense? Okay, so we know what k-means does. Here's what k-means does, right? So k-means has, let's see, an assignment step. Assignment step. where Ci is equal to argmin over j of xi minus mu c mu j. Thank you. Right, so compute the distance of xi from every single cluster center. Take the argument, store that in Ci. Right, that's this discrete variable. Right, and AI is random also that right? So that's the assignment step. And the second step was sort of the recentering step. Recentering step where what we said was you take, so every mu j, you already know which data points are assigned to cluster center j, and so you basically re-estimate their means, right? So it's just 1 over the number of points assigned to j divided by sum over xi, and another way of saying this is I such that aij is equal to 1. Right, so basically take a mean of the data points where aij is equal to 1. Sum over those i's such that aij is 1. Does that make sense? Just a fancy way of saying take an average. Take an average, vector averages, take an average, recenter, take an average, reassign, take an average, reassign, hope for convergence, call it a day. Does that make sense? Any questions so far? Yes?
So, like, is there a possibility where two cluster centers you initialized end up being in the, like, being very close to each other in the same cluster?
So two cluster centers end up being very close to each other, okay.
Like after convergence, basically.
So can it ever, I think the question that you're asking is, can it ever happen that a cluster becomes dead, so it never gets assigned, right? Because if they're too close, one of them can take all data points and the other one will never be assigned. Yes, it can happen. There are a whole bunch of these boundary cases that so if you type help k-means in MATLAB, it'll actually tell you that you have to assign how to take care of these boundary cases, because you can have these clusters that essentially die off because this argument never picks that cluster center, and therefore you cannot estimate the mean of those points. And so you either have to reinitialize or you have to accept that your k-means algorithm will give you clusters which are less than k. Yes. Okay. So that's an algorithm. Now we have to ask questions like, what does this algorithm mean? Does it converge? What is it trying to do? So let's start with the easy one. Does it converge? Do people think that converges?
No.
Not always. Why do you say that?
If you have too many K's, not enough.
So if you have too many K's,
The other way around, not enough K's might go between one cluster and the other.
if you have too little K's, this you think might go around between, jump around between two different cluster assignments. Okay. So this is, anybody else think otherwise?
I don't think this is the main problem. I guess the condition of data sets. You could find a condition of clusters that
Where
makes
it
this
won't
loop forever.
So you can find a data set where it won't converge.
Yes.
Okay. So this is actually one of the reasons why, when you're trying to analyze, is this procedure going to stop? It's a good idea to ask yourself, what is this procedure doing or optimizing, right? So let's look at a demo. Let's see whether things actually converge or not. Here's my k-means demo. So let's put in some points, right? And notice I will strategically make the problem extremely easy for k-means, right? If you know the assumptions involved in k-means, you're sort of aware of what I'm cheating a bit. I'm sort of making this is an extremely easy clustering problem. The clusters seem to be very nicely spread apart. The sort of it's very clear visually that there should be 3 clusters here. The inter-cluster distances here are small. The intra-cluster distances are small. The inter-cluster distances are large. So I'm sort of cheating a bit. But I can try to do what Harsh suggested, right? I can sort of initialize all 3 clusters roughly here. Just vanished. Oh, perfect. Anyway, so if you do that, and let me track history, here's your initialization of the thing, right? Your first step, this is the assignment of data points. So this is the green cluster center, and all of these are shaded according to which one of them they pick. So this one actually does end up picking this one actually ends up picking, for some odd reason, I'm not exactly sure. But something that seems a little wrong. Okay, maybe I'm not viewing something. These ones are blue, those ones are brownish. Right? So this is the cluster assignment step. I take the next step. This is the new means that are estimated, right? Of all these points, it moved to the new mean, and it has done the reassignment of data points. So now these ones are blue, these ones are brown, these ones are green. That's one iteration. And another iteration. So it actually, now that it knows that these were the only brown points, there was 1 point here. So now that these are the only brown points, this is the new mean estimated. And there are sort of slight changes to these guys and these guys as well. And at this point, you're essentially done. Why are you done? Because the same labels got estimated for every data point, therefore same clusters. Yes?
With respect to that, I have a question. First, the last time, right, it had the same labels. I mean, how say this? You just stop on this one.
Yeah.
Because the labels didn't change. So you
Yeah.
actually used the last step, actually. I mean, you don't, I mean, the previous step have the same labels, but you don't actually use the previous step. You use the new one, right?
Right. I mean, you stop when, in every iteration, you're checking the cluster assignment variables. If the previous iteration had the same cluster assignment, you can stop them. And whether you estimate mean this time or last time, it's the same.
Then that's pretty much the same as checking if there is any change, because it's impossible to have any change because you will be averaging, you will be able to find the means on the same points.
Right. Exactly. So if there is no change in assignment variables, there will be no change in the means that are assigned. Right? Okay. So the point here was, it's actually yours. Yes.
So if you select different K,
Yeah.
the effect will be very different. How can you measure the difference between them?
How can you measure? Excellent. So this is, again, where it comes in. What is the objective function here, right? So the task loss in supervised learning is a really nice thing because it lets you say, here's what I care about. In k-means, it's very difficult to say, what do you care about? It's one of those things where I know a good cluster when I see it. Maybe I'm trying to do data exploration. Maybe I'm trying to learn something from the data. How can I tell you what I want to see? Right? So if you think about you're an ad company, right? There's a bunch of people searching or visiting your website. You'd like to know what are those types of people. You don't actually know what those types are. You're trying to do discovery. It's very difficult to write down when an algorithm got that right, because you don't know what you're trying to get to in the first place. Right? So that notion makes it difficult to compare. We will, in a second, write down an objective function that k-means is optimizing, and we will say that this objective function, I can use that to tell whether it's a good clustering or a bad clustering. Unfortunately, that objective function will have a pathological behavior in the sense that larger number of clusters will always be nice under that objective. We talk about this. Yes?
Also, I feel that the initializing the centers has a very big importance. So if we initialize them to like some other location.
Not here. So in this case, it won't be the case. So can I? Oh man.
So can there's initialize them all like to the corner on the left, for example.
Oh, thank you. So where would you like them to be?
Like
Here?
that, yeah.
It's not that far. So then here?
No, all of them.
All of
No, like
them.
all of them.
them.
Yeah.
Oh.
No, make it
Start, step. Oh, we're stuck. How about if there was a slight difference between the three, but not overlapping? Start. Oh, so here's what's happening, right? At the first, okay. Thank you, that's an excellent point. But here's what's happening. If you notice, all of them have the same color. Two of your cluster centers are dead in this implementation, right? So if you open up MATLAB, for example, one of the things it asks you is how do you want to handle when a cluster dies? And there are a few options. If you're okay with less than k, then you just do what this demo is doing, in which case you'll end up with one cluster. That's fine. And the other option that MATLAB allows you to do is when a cluster dies, I will randomly initialize that cluster center somewhere else and start the algorithm there. In that case, you will sort of try to keep clusters alive and sort of have a different random initialization. The third thing you could do is you could try to force that no, every cluster needs to get at least 1 point. Right? So you modify your mins so that every cluster takes at least one data point that is closest to it, in which case it can't die. Does that make sense? Interesting. You guys are good at pathological. We're alive. Okay, so they get a, sorry, let me reset that. So one iteration, you take a step, you get here, another step. So at this point, perfect cluster. K-means is actually, even though I'm posing the question, does K-means converge? And it seems like from this is proof by demonstration. We tried 5 demos, it always converged, therefore it must always converge. The problem with K-means, incidentally, is not that it may not converge, which we'll actually prove, Chris, and we'll show that statement wrong. The K-means always converges. In fact, the typical problem with K-means is that it converges too early. That it's a very quote-unquote sticky algorithm. Wherever you initialize, it will very quickly stop, and so initialization does become key. Okay. So this was sort of a demonstration just to give you another example of what happens if you sort of have too large a K. So here, a few clusters are dead, but we have 4 still surviving right now, and this is so this cluster died. Well, one of them died.
Just one died.
Yeah, that one died, but you ended up basically fragmenting this cluster into 2. There's sort of one blue cluster here, there's one green cluster here, there's sort of one light bluish, light dark. 2 different blues or same blue? No, it's 2 different.
It can be the same.
Yeah, it's 2 different blues. There's one cluster here, there's one cluster here. So you can imagine what would happen with a large K, what would happen with a small K, right? At small K, you're sort of merging clusters together as large K. Okay. So that's good. Now that we've done that, let's sort of get a little bit more math now. So K-means does something, and I'd like to know what is K-means optimizing. So here's an objective function that I claim K-means is optimizing. So I need this. So this is f of mu1 to mu k, c1 to cn. Here's an objective function. Go to every single data point and measure the okay. So here's an objective function, right? Go to every single data point and measure the distance between that data point and the cluster center to which you have assigned it. Does that make sense? Which is also the same thing as saying, by the way, that I equals 1 to n, j equals 1 to k of aij xi minus bj. This is sort of, I have to bury this into a subscript notation, so pick the cluster center that you assign. This is sort of a little nicer and cleaner. I multiply aij, so every pair of data point I cluster j, but I know this quantity will be 0 for what you're not assigned to do. So you're only pulling out the term that is actually good. Okay, so this is, think of this as a distortion function. Think of k-means as a really, really bad compression algorithm, right? It sort of takes a bunch of data points, and what k-means does is it says, I will replace these data points. I will replace each one of these data points with a cluster center. Here's my cluster center, and I will replace each of these data points with this cluster center. And here's the distortion that happens in your data set. By replacing this xi with xc, that's the distortion. You're actually measuring for every data point what is the distance from this data point to the cluster center to which you have assigned. Does that make sense? And so this is a bad clustering because the sum of distances is large. If you had placed this cluster center somewhere here, there would be a good cluster. Right? With that view that this is sort of a distortion function, now this actually tells us how to measure the quality of a cluster. Right? Low numbers are good, high numbers are large, high numbers are bad. Does that make sense? And so the optimal clustering, if you will, does this, right? So this is what we'd like. U1 through nu k and min over C1 to Cn or A1 to k. Does that make sense? So this is formally the optimization problem that you're interested in. The solution to this is a good clustering. With me so far?
Yes.
So it should be clear that there's a little bit of, you have to be careful. So coming back to Zili's question, right? Can we tell, so when you have the same k, it makes sense to compare this objective. But what happens as I increase k to that objective?
You can make k equal to n and get 0.
Perfect. You can always make k equals n. So to every data point, you can assign its own cluster center, right? Here. Every data point becomes its own cluster center, and you can drive down this compression loss to 0. That's why this sort of compression view is important. That makes sense? So if I plot on the x-axis sort of k that you have chosen, and on the y-axis the quality of compression achieved by the optimal compression algorithm, you will sort of see this sort of a behavior, right? Notice that this is the quality of the optimal compression algorithm. If you actually ran k-means, you may actually see a bumpy behavior. Why? Because k-means can't solve this problem optimally. Right? K-means will show as an approximate optimization algorithm for this problem. Does that make sense so far? Yes.
What do you mean with minimizing C1, Cn?
So these are variables, right? They're discrete variables. Take every data point and tell me which 1 through k, what would you like to assign it to? And these are continuous variables. So place cluster centers somewhere, assign data points somewhere. So think of this as like n numbers that you have to choose, each between 1 through k. And a good assignment is one where you should assign a data point to things that are closest to it, right? But you can make a bad assignment. Does that make sense? Okay, so this is the optimization problem that we're interested in. This is an optimal clustering, and this tells us the quality of the clustering. And we have to keep this view in mind, because this tells us that you can always do better at clustering by having larger k under this objective function. But therefore, this objective function is really not, it's just a convenient mathematical choice. It's not what makes for a good clustering. Right? Does that make sense? Because clearly this case of assigning every data point to its own cluster isn't helpful if you're trying to do discovery. If you're really interested in knowing how many types of users come to your website, telling you that there's a 6 billion types of users that come to your website isn't really all that fine. You're technically correct, but useless. Right? So this is going to be a problem in general in unsupervised learning algorithms. This is why there's a bunch of different kinds of clustering algorithms, each one defining its own objective function, because they're trying to claim that that objective function matches human judgment vector of what is the output of the minimization under that objective function. Does that make sense? Yes?
Can't we have a regularization term for k?
You could have a regularization term for k. In fact, that's sometimes often done. And you can sort of, there's going to be a Bayesian view of clustering, right? In which k is a parameter and you can have sort of priors on k. But you're still sort of, what is the optimal prior? Like, where does that come from?
Yeah, so similar kind of question. Why can't we have one more term added in the objective function that kinds of wants different cluster centers to be far off? The distance between.
Why is there no diversity term here? Yes, it's actually implicit. So you don't have to force a term that says cluster centers should be different, because this sort of an objective, you actually hurt yourself by not placing the cluster centers apart. So it's actually implicit in the objective. An algorithm that places the cluster centers near the modes of the density will do better under that objective. Yes. Any other questions? Okay. So this is what we want to solve, and this is at this point becoming quite common practice in machine learning class. We cannot solve that optimally, right? That's a mixed, discrete, continuous optimization problem. These variables are discrete. These variables are continuous. That's really hard. It's not going to happen. What we can do is set up something called a coordinate descent algorithm. Anybody heard of coordinate descent? Nobody. Okay. So a coordinate descent algorithm is an algorithm where it sort of essentially looks like this. If you have a function that depends on two variables, often what you try to do is if I hold A fixed, I can minimize B to completion. And if I hold B fixed, I can minimize A to completion. This is called a coordinate descent because this is a coordinate and this is another coordinate, and you're taking a descent step, or you're basically optimizing one coordinate at a time. Does that make sense? And what we're trying to do here, if you try to map it to k-means, is that this is called a block coordinate descent algorithm. There's this block of variables and this block of variables. If you tell me what these block of variables are, or if you hold them fixed, I can optimize these to completion. And if you tell me what these blockers, I can optimize these to completion. The reason why you'd like to make this connection to coordinate descent is that for bounded functions that take discrete values, coordinate descent will always converge. So one way of thinking that is, so f of a comma b, if your algorithm looks like this, min over a of f of a comma, so at time t, so dt, min over a, and this is, let's say ad, and min of f of a t, b, and let's say that's b, so I'll say t minus 1, and does that make sense? It's just formally saying, use your last initialization of b, minimize a to completion, that's your next iterate. Hold that fixed, minimize b to completion, that's your next iterate. Right? Both steps can only reduce your objective function. Right? B is fixed, a is being minimized, so your objective function only reduces. A is fixed, b is minimized, so your objective function only reduces. So in each step of your algorithm, the objective function can only go down, and if the objective function is bounded, there's only so many times it can go down. We'll stop in a second as soon as I get this done. So is our objective function bounded from below? Can it go to negative infinity? No, it can only go to 0. So your objective function is bounded. It cannot go below 0. Each step of the optimization algorithm reduces the objective, and crucially, you have a discrete variable in here. So it only has some finite number of states. You will not cycle through states. That's the key thing. This is a discrete variable. It has some finite number of states. They may be exponentially large, but they're finite. And you will never visit the same state twice, because in each iteration you're decreasing the objective function. Does that make sense? So that's sort of the argument for why k-means will always converge. Okay, let's take a minute here.
Would be good, like at least Sometimes I'm like, why did I switch? Because when I'm too far along, I can't go back. I'm sort of getting whatever I'm like, how much mine make a great paycheck. Those two, like, everything goes out pretty much. Yeah.
We work for 6
Me too, that's, you know, it's like, no big deal. It's like, way easier. I'm like,
就是单调可能有商业这系列研究。
yeah, which is nice. When you're going to work, exactly. Like, yeah, it's only grad school. Right. Like,
整个三后再可能继续。
no. Don't understand. Anyways, yeah. But I think 2 years left.
Okay, so there seems to be some lingering confusion, so what I'll do is I'll actually write down these two steps in terms of mu's and c's, and you'll see that the same two things pop up. Okay? I'll do a stuff. Yeah.
It's there, so there is two kind of minimization, over C and over mu.
Yeah.
So is there one-to-one match, like minimizing over C is like finding the centroid and
The other way around. So minimize. Let me do that. So the minimization over C is the cluster assignment step, and minimization over mu is the centroid. Okay. So let me just do that because there seems to be some confusion. Let's do the first things first. So fix mu1 through mu k and minimize over c1 through cn. Right? That's one block. Pick a block of coordinates, fix them, pick the other block, minimize over them. Right? So we're trying to minimize this sort of a function. Let's do mu's are given. Okay, let's do this. Right? So right, this is minimization of over c1 through cn of summation of I equals 1 through n of xi minus mu of ci. Right? Notice that I'm taking the first line from the definition there. Very quickly you notice that even though there are n variables here, there's a summation of n terms and they're all sort of decoupled. Every term only depends on the choice that you make at xi. Right? So I can basically swap this summation and minimization. Right? Because every term only depends on one thing. So this is basically I equals 1 through n min over ci of xi minus mu ci norm square. Right? And that's pretty clear. So there are, for every variable, you have k choices here. What you're going to do is compute the distance of cluster center 1, 2, 3, 4 all the way till k minus x. And what are you going to end up picking here? The closest cluster center. Right? So this is the assignment step. Right? So the coordinate descent, fix mu, minimize c is the assignment step. And now we're going to do the next one where you fix c's, minimize over mu, and that's going to be the clustering step. I mean the cluster center estimation step. Fix C1 to Cn and minimize mu1 to mu k. And for this, what I'll do is I'll take the second line there because this is actually an easier form for me to deal with. Right? It doesn't really matter. As soon as you know the CIs, you know the AI is one. So it's going to be min over mu1 to mu k summation over I, summation over j, aij xi minus mu j norm squared. The first trick to do is I'll basically swap the two summations I and j. Why? Because there's a bunch of cluster centers. If I can convert them into their own independent problems, that would be really nice. Okay. So I'll just make this summed over j from 1 to k, summed over I from 1 to n. The same thing. Yes?
Can you repeat why you switched?
So the reason I switched is because the math is going to become easier in a step. The question that you should be asking is why can you switch? The reason why you can switch is think of this as a counting argument. There's I is going down and there's j going down, and every interaction of those two terms is actually present in that sum. So whether I count along the rows or I count along the columns, it doesn't really change the summation of the counting argument. So I can swap summations like that. And as soon as I make that swap, there's a bunch of minimizations that I can pull in, because the thing to notice here is, right, I'm going to minimize according to mu j. Right, mu j's are my variables. Each one of these terms only depends on a single mu j. Does that make sense? So what I can do is I can do a summation j equals 1 to k min over mu j, and then there's a summation I equals 1 to n aij, and another slight trick, mu j minus xi. Just swapping the order of that. And I can do that because it's square count. Okay, so here's the problem that you need to solve. This is the optimization problem. Anybody recognize the optimization problem? These squares, but it's sort of like extremely simple form of these squares. This is the centroid problem, right? There's a bunch of points given to you, x1 through xn, and you're asked to pick one point, mu j, right? So this is all happening for j. So forget the mu j, right? And the other thing I can do is aij is all zeros and ones, right? And I know that, so I can just sum over all i's. I can just sum over the i's that have aij set to 1. Right, so I tell you which points are in this cluster center, and you are supposed to minimize the squared distance, the sum of squared distance to each one of them. This is the centroid problem, and the answer to this, like if you take the gradient of this with respect to mu j and set it equal to 0, there's a mu j terms that survives, and there's an xi terms that survives. It ends up becomes an averaging thing. And so if you take the gradient set it equal to 0, the mu j star that you get is mean of all these xi's, where aij equals 1. Does that make sense? Which is exactly the recentering step. So the reason why the recentering step fits into this coordinate descent is because minimization over sum of squared of a bunch of points is basically the centroid problem, and you get the mean of those points. Does that make sense? So now you just have to alternate, right? Find the means, do the assignment again, find the means, do the assignment again. At each point of time, if you compute this objective function, it's only going down. Because at each point of time, you're minimizing over some set of variables, you can only improve the objective. That makes sense? Okay. Okay, so we have an algorithmic sort of procedural view of k-means. We connected that to sort of these two steps, an assignment step and a recentering step, where you find them in assignment, recenter the things, and we've sort of connected it to this sort of an objective, a compression objective. Yes, basically represent each point by its cluster center, how much do I lose in the distances, right? And coordinate descent in that objective basically gives you k-means. You write down your whole objective over mu's and a's, fix one of them, optimize the other one, and you get basically the same steps. Okay, these things actually are used a lot. So how is k-means used, or why is k-means used? It's actually used a lot in practice in, for example, in computer vision problems called bag of words. So if you remember, I told you about the bag of words in text, where you take a document and you represent it as a histogram of words, where these are coming from some dictionary. In computer vision, it's not always clear what these words are because you don't have a dictionary of words, and so what people do is they sort of create a bag of, if you will, of visual words. They take patches of images that you should represent these things at. And the way to sort of, so for example, you will have, this is your visual dictionary, you have parts of objects, and you can represent each object as sort of a histogram over these parts. But where do these parts come from? Where do these visual words come from? The way these things are done is you'll basically take images, detect certain key points, extract certain feature vectors, and this is what people study in the computer vision class, something like a SIF descriptor at every key point, or you can just basically take a window and scan it across the image and take the RGB values, right, for each patch. So you make a large data set where on each column is feature vector extracted at that patch, and you sort of put it in some a high dimensional space. There should be some feature vectors extracted each patch. Each point here is coming from some patch in an image, and you run sort of k-means algorithm, and it tells you here's one cluster, here's another cluster, here's another cluster. Right? And this process in computer vision is often sometimes called vector quantization, but it's the same thing. And often when you look at these visualizations, this is what sort of the clustered patches often look like, right? They often look like sort of oriented edges and sort of curved shapes and things like that. So you can think of this as a vocabulary, a dictionary of visual words where you'd like to express an object as, it mentions this word 10 times and then it mentions this word 20 times and so on. Right? But k-means is what is giving you those things. And just like in a regular sort of dictionary, you have concepts of synonyms and polysemy, you also end up having that in sort of this sort of thing, right? So here's visual polysemy, which means that two different concepts are mapped to the same cluster. Right? So it's a single cluster which represents this, which is the end point of a motorbike, and this, which is the tip of a plane. But when you look at a patch, it roughly all looks the same, and that's why they all get clustered into the same thing. Right? So this is just like in English, you have sometimes the same word having multiple meanings. This is what that is representing. And just like in English, you have the concept of synonyms, so two different words having the same meanings. This is also what happens in sort of visual words, if you will. You have two different clusters that are both basically representing a part of an object, in this case, a wheel. Does that make sense? So sort of connecting concepts or under-clustering or over-clustering to concepts in sort of language. And typically what you do is you sort of represent an image as a histogram over these words, but the role of k-means was in picking these words. Does that make sense? Mm-hmm. Okay. So let's make k-means fail. And in doing that, it will expose something that we need. So how many clusters are here, and what are those clustering structures? Yes?
I would say there's one small one within a larger one.
One small one within a larger one. Sure. So we haven't actually talked about hierarchical clustering, but yes, that would be one way of going. Where there's a tree-structured clustering, and it can be part of the lower levels in the hierarchy or higher levels of the hierarchy. But even without going there, it's clear that in some data sets, it's unclear what the cluster structure is, how many clusters to choose. But even more than that, some clusters are just not nice spherical objects, right? They may be elongated objects. The best way of thinking about this is, here's that demo I sort of began. Oh no, reset, how do I reset? So here's one thing that I claim to be a cluster, and maybe here's another sort of mini cluster. And if I initialize two different clusters like that, and of course I get to pick all the parameters, so maybe this demo will work. If I do start, step, oh, it actually did work. Let's try again, that one. Start, step, excellent. So here's the converged result of k-means for that particular initialization, right? So you notice that different initializations will get stuck in different sort of local minima, but here's one initialization where it does in particular really bad. One of the reasons why it does bad is if you notice there was a particular choice that we were making in k-means. How are we doing reassignment? What particular distance were we using? L2, excellent. So L2 rewards each dimension equally, right? But if you know something about your data, that there's one dimension where variance is larger, and this is an idea that we've met before. Like this idea of monomodal distances, and somehow if you know something about your data, you should be using a different distance vector. And here's an algorithm that we are going to, I'm going to make this guy stop.
The previous demo is using the same objective function without regularization term or anything.
Yeah.
Yeah.
So you mean with this particular demo?
Yeah.
It's, yes, you're using the same, well, I mean, I believe it's using the same, I haven't seen the source code, but I think it's doing the same thing. Okay, excellent. So here's a similar, I can't replicate the thing, but here's a similar sort of similar diagram. Do and run. Here's a different sort of clustering algorithm. This one, we're going to talk about this next. It's called a Gaussian mixture model. It not only estimates a cluster center and a cluster assignment, it actually estimates something called covariance matrices, right? So for each of these clusters or Gaussians, it's going to estimate these full covariance matrices. Therefore, it can handle the fact that the distance metric that you end up using is not identity or diagonal. Right? So you can sort of fit these things. This is one Gaussian or this is another Gaussian. In fact, one of the things that it also does, it relaxes the hard assignment. So every data point can only be in one cluster to a soft assignment. That makes sense? Okay. So let's go there. All right. So this is an idea called Gaussian mixture models or GMMs, and it generally arises from the fact. So this is where clustering sort of blends into density estimation. It's this idea that I have some data, this is what the histogram of that data looks like, this is one-dimensional data, and what I'd like to do is, you can think of it as dividing this into clusters, or you can think of this as fitting a distribution to this, right? Find me some distribution. We only want to stick in the land of Gaussians. It's a very nice sort of convenient place. However, the data clearly tells us that this should not be a Gaussian, right? There's a multimodal structure. So the obvious answer is more Gaussians, right? So we're going to talk about mixture of Gaussians, or, in specifically multivariate Gaussians. So here, for example, the illustration that I was trying to draw was a mixture of two Gaussians here, but we're going to go to higher dimensions. So this is dimension 1, this is dimension 2, marginals are also Gaussians, and this is the joint Gaussian. It can have sort of a covariance structure. Right? So this is a top-down view of three Gaussians. The circle, the ellipses are indicating points which have the same probability assigned to them under that Gaussian. Right? So these are the sort of probability contours. And here is sort of a density function, a three-dimensional plot of that, which is a combination of these three Gaussians, each one giving a single peak to this. Does that make sense? So the goal is going to be, given a bunch of data points, in a one-dimensional case it will look like this, given a bunch of data points, right? Fit a bunch of Gaussians, k Gaussians if you will, and we're purposely using similar notation because soon we'll compare k-means to Gaussian mixed models. Fit k Gaussians, and by fitting I mean estimate the mean variables and also estimate the covariance matrices. Right? So the means are going to be some d-dimensional vectors, and the covariance matrices are going to be d by d-dimensional matrices. Does that make sense? So estimate that for this, estimate that for this, estimate that for this. Okay, so let me write that down notationally, and then let's go from there.
reminds me of the Fourier series, the mixture of Gaussians. Right?
What does it remind you of?
Fourier series, so you can represent any signal as a sum of a bunch of
Yeah.
sine waves.
Yeah, so there's going to be a similar idea. If you use enough Gaussians, you can estimate any distribution to any decision. Yeah. I don't know if there's a precise connection there. I'll have to look into that. Whether you can actually express that with a Fourier proof and something. All right. So here's the task that we're dealing with. So if you think about, if in a single sentence, if k-means was about show me the types of my input, Gaussian mixture models are about fit a distribution or a collection of Gaussians, right? And soon we'll make that connection between the two precise. But here's going to be the goal. You're given a data set, again containing x1 to xn, and you're asked to basically fit a distribution p of x. We know p of x, a single Gaussian won't do, so we'd like to do a collection of Gaussians. The way we're going to do that, and this is an extremely common sort of notational and mathematical trick, is you think of a new variable, introducing a new variable called a hidden variable. This is called a hidden variable or a latent variable. It's a hidden or latent variable z that basically z indexes 1 through k, and z is a discrete variable that tells you which Gaussian you're sort of coming from, if you will. That's one way of thinking about it. That's not a very precise way of thinking about it, because this is a sort of a density estimation task. There is no single Gaussian that this data point originated from, right? But you can think of, if you want to think about sampling in this, creating a new data set from this task, you think of first I choose a Gaussian, then I sample from that Gaussian. Here's sort of a formalization of this. This is our probabilistic Gaussian mixture model. It says z is a categorical variable with some parameter pi, right? So that's just some distribution, and what this essentially means that the probability of z equals c is some pi c. It's just some number. So pi c is greater than or equal to 0, and the sum of pi c from c equals 1 to k is 1. It's just some categorical distribution. And the second thing that you do is x given z equals c is a normal from some mu c from a covariance matrix, sigma c. And what this basically means is, the PDF of x equals little x given z equals c is 1 over 2 pi to the d over 2, the determinant of pi c square root e to the negative x minus mu c sigma c inverse x minus right. All that's really saying is this is a multivariate Gaussian. A long way of saying that. There's a multivariate Gaussian with some mean parameter mu and some covariance matrix sigma c. The mean parameter lives in sigma d, and the sigma is in sigma d plus c. And it's actually positive semi-definite, but let's ignore that. Does that make sense? Just a multivariate norm. As in the previous k-means case, for any particular data point, nobody tells you which Gaussian is taking responsibility for that data point. So under this model, if someone asks you what is the probability of x equals little x, then what you have to do is you have to sum over all assignments to z. Right? You have to marginalize out the random variable that you have not seen, and therefore this is the joint distribution marginalized out over z, and that's what tells me my marginal probability of x. Does that make sense? And that's c equals 1 through k probability of x equals little x given z equals c times probability of z equals c. Right, just chain rule. And if I just use the numbers defined there, it's pi c times normal of mu c comma sigma c. Right? So this part is pi c, this part is that normal that we just wrote down. The probability of x, if you tell me which Gaussian it's coming from, it's just some normal. Right? And this is why it's called a Gaussian mixture model. Right? There's a bunch of Gaussians and you're combining them with some convex combination. Right? Pi c is a distribution that sums to 1, so this is a convex combination of these Gaussians that lead you to your density function. Does that make sense? Okay. So the goal in Gaussian mixture models or density estimation is there's a bunch of these parameters, right? There are z parameters here, the pi parameters here, the mu parameters here, and the sigma parameters here. If you try to map this in your head to k-means, there's an analog. This parameter is exactly the cluster center. We were not estimating the covariance matrices of the clusters, right? In fact, if you stare at this and squint a little, there was an identity assumption somewhere being made. This is not something that you met there as well. This is a new thing. Right? So these three together are the theta parameters that you'd like to estimate. Right? Given a data set, find me a theta parameter at this point, sort of something should be going. MLE, thank you. How long do we do coin toss experiment, right? So the standard we're doing, which we'll not do today, but sort of here's what you will end up doing. This is going to be theta star is going to be arg max of probability. So summation maximum likelihood. So you write down product I equals 1 to n of probability of x equals x y given theta. Right? If I put my cluster centers here, if I make, if I use these covariance matrices, those priors, what probability is assigned to this data set? Right? And I'd like to choose my parameters which make this data set really likely. Right? If I go place my Gaussian somewhere out in the extreme, like he was suggesting, right? Go place the cluster center out in the corners. By the time you get to the data points, the probabilities are assigned to 0, right? And so that's not a good thing to do. So this is what we'll do as just summation I equals 1 to n log probability of x equals to xi given theta. So if you can do this argmax, that's how you would find these mu, sigma, and pi parameters. We'll tell you next time how to find them, but today what I'll tell you is sort of conflicting messages. I showed you a demo that clearly it can be done, right? That website was solving it. But I'll try to sort of nail this into your head that this is a difficult problem. It shouldn't be possible to do this. Right? This is an extremely sort of ill-conditioned problem, if you will. Okay, so let me try to convince you of why is this hard. So there are three reasons why this is hard. The first one I'll actually skip over. I'll go into details next time. But the reason why it becomes hard is this term right here. There's a log probability. And this probability we don't know, right? We're going to have to write a z, and we're going to have to sum over all z's, right? So there's going to be a summation here that's going to sit inside the log. And that's going to be a problem. Sum of logs is great. Log of sums is extremely problematic because what that's going to do is it's not going to factorize. It means all of your parameters get coupled together. It means you cannot estimate the parameters of one Gaussian separate from another Gaussian because they're all sort of sitting inside a log. Changing one affects the other one. And I'll make this more precise next time. Right? So that is difficult already. But there's a second problem, which is called the identifiability problem. If you stare at this simple case, this is a one-dimensional data set. We want to fit two Gaussians. This should be trivial. Right? In your head, you can see what those two Gaussians should be. There should be a cluster center, a Gaussian center here, there should be a Gaussian center here, maybe you estimate some variances. One-dimensional variances, it shouldn't be hard. Does anybody see the problem why it might be difficult? Here's a picture that might help. This is that data set. This is on the x-axis mu1, so you can place cluster center anywhere here. This is mu2, so you can place the second cluster somewhere, right? This is a two-dimensional, and it's showing you a heat map of how much probability is assigned to this data set as a function of mu1 and mu2. And there, it's clear that there are two peaks. It's because you can place mu1 here and mu2 here, or you can place mu2 here and mu1 here. There's an entire permutation of your cluster because there is no, cluster number 1 doesn't mean anything. This is what differentiates classification from clustering. Right? If this was class 1, it's not like I could have called this class 1 and my score would be just about the same, right? You would do worse than chance, so you could fix it, but this sort of an objective function is highly problematic. You can place mu1 here, mu2 here, or the other way around, and there are two identical peaks, so there's a whole bunch of symmetries in the problem. There's only two clusters, but if you had k clusters, there's an entire k permutation that is going to have the same objective function. So this objective clearly cannot be convex, because if there's one peak, there's k permutation of other peaks as well. Does that make sense? So this is problematic. It's not just, oh, I don't know what cluster 1 is, all permutations are the same. It's just that objective function is highly non-convex, right, because of that. That makes sense? This feels like you should still be able to handle it because all peaks are of equal height, right? So, okay, are you sure this is really a problem, or is this just bothering mathematicians? But that's not the only thing. Here's another problem. Here's a problem number 3. There's one-dimensional data. There's two Gaussians again to be fit. What if I fit an extremely peaky Gaussian to one point and a flat Gaussian to everything else? Anybody see what would happen in that case?
So about the boundary, what will happen?
I'm sorry?
And about the boundary between these two Gaussians,
Yeah.
the intersection, if I sample at this point, what will happen?
Nothing. So you can obviously sample and create more data points, but we're still talking about log likelihood of this data set under these two Gaussians, right? So this is the only data set that's available to me right now. The way I'm finding my parameters is I'm writing down log likelihood of that data set, and I'm trying to maximize that log likelihood. And I'm trying to show that log likelihood has this really odd behavior, right? So yes, you could sample new data points, and it will give you reasonable looking or maybe some messy samples, but that's not really the problem here. The problem here is, let me say that I will take one of my cluster centers, and I will actually collapse it to a data point x1, right? Now what happens, what is the probability or PDF value that gets assigned?
What do you mean collapse?
What?
What do you mean by?
What do I mean by collapse? So for now, let me just say that I will set the mean for cluster 1 on this one data point. So far I haven't said anything about covariance. Let's work in this one-dimensional space, very simple space, right? So let me not use the vector signs, right? Everything's one-dimensional, right? This is 1 over square root 2 pi sigma squared e to the negative of x minus mu squared by 2 sigma squared. If you set the mu equals x1, this becomes e to the 0, right? For all values of sigma, it becomes e to the 0. And so this thing is just 1, always, for all values of sigma. And so it's 1 over square root 2 pi sigma squared. So my probability, if I start making sigma approach 0, and that's the trick, I keep calling it probability, it's not probability, it's the density value, right? And that is going to infinity. Right? So this PDF is going to infinity if your sigma is going to 0. So you take one Gaussian and you collapse it on this one data point, and you have one other Gaussian that's providing some value. Does that make sense? So it takes your log likelihood to infinity. Does that make sense? Why does it happen? Because these are continuous distributions, so PDFs aren't bounded by 1. PDFs can go to infinity. What's happening is that one data point is becoming super confident, so it's assigning infinite sort of likelihood to one data point. So that function map that I showed you doesn't actually look like that. somewhere in this field are spikes that suddenly go to infinity, and not just one spike. Every time there's a spike, there's a permutation of those things, right? You can take a Gaussian one, make it collapse on any of the n data points. You can take 2 Gaussians, make them collapse on 1 and 2 data points. You can take 3 Gaussians, make them collapse on 1, 2, or 3 data points. Do you get where I'm going? This objective map has a bunch of spikes that are suddenly going to infinity. And we are nicely saying, well, go ahead and maximize this. And wherever you stop, that's the sort of mean and variance parameters. Right. So it's an extremely ill-conditioned objective, but we're able to maximize it. And in fact, next time what we'll prove is you've kind of already maximized it. K-means can be viewed as maximizing likelihood under a particular set of assumptions. So we already have an algorithm that's able to do. Let's stop there.